So what this algorithm does is, I told you every algorithm has inbuilt optimization function. Linear model has gradient descent. This model uses a function called Logloss. It minimizes this Logloss, and to minimize the Logloss, can you guess what it manipulates? It again manipulates this M and C. It looks for the right line, which when converted into S curve will minimize the overall misclassifications. The objective is to minimize misclassifications. To minimize misclassification, it has to find out what line is the best line, which when I convert into the S curve will minimize my misclassifications. That function is called Logloss function. What I'm showing here is same example which I took here. So I'm seeing some kind of clustering, some kind of pattern, and the density distribution of the two classes is overlapping, but like this. So can I make use of this and create my model? Yes, the first attempt is the y-axis is my probability, and probability depends on how far away on the x-axis you are. So the vertical axis is the probability of somebody being non-defaulter. If this was probability of something be defaulter, then this S curve will be ulta. It will be like this. Okay? So it doesn't matter which one you take. I've taken this one because it's more intuitive to explain. So we are looking for an S curve which will do the clean separation of the two. Now let us interpret this model. What this model is telling you is, for a given value of x, suppose this is the value, x value, your model is saying the probability of him being non-defaulter is very high. Anything beyond 0.5 cutoff is very high. That means this guy is going to be a non-defaulter. On the lower income side, take any value x. What the model is saying is, for this guy, the probability of him being non-defaulter is very low, so he's likely to be a defaulter. That's what this model is saying. So in your training set, you have, suppose if you, in the training set, suppose you have a red point here, you know he's a defaulter. You know he's a defaulter, you already have the labels with you. But the model is saying his probability of being non-defaulter is very high, so model is saying he's a non-defaulter. So red point is getting classified as non-defaulter. This is a mistake. On the other hand, you have a green point here. You know he's a good guy. He's paid back his loan, but what your model is saying is he's likely to be a defaulter. Again, it's doing a mistake here. These two are mistakes. Correct. Take any blue point. Take any of these points, the green point. Your model is saying he's likely to be a non-defaulter, and he's actually a non-defaulter. Your model is not doing any mistake. It's doing a good job. Same way, take the other one. As per your model, he's likely to be a defaulter, and he is a defaulter. It's doing correct predictions. Now, by shifting this curve, see, as long as you talk about this end or that end, there is no problem. The problem comes in the overlap region where the two classes overlap. That is where the misclassification happens. So by controlling the M and the C, I lift the curve up, I move the curve forward and backward, I change the slope of the curve, I do everything possible to ensure that all the greens get identified as green, all the reds get identified as red. That is what I try to achieve by controlling the slope and the C. This is the kind of picture you will come across in the books and articles when you read. And what you will see is, yeah, they have shown the S curve. They have shown the S curve here, right? Now, when I first time saw it, I couldn't understand what the curve is saying. But then subsequently I realized they shouldn't have shown these blue points. The blue point should have been shown here. Okay. As per the model, the point belongs to blue, but actually he's red. Look at the red points. These are misclassified points. As per the model, the red point belongs to the blue class, but actually he's red. These are all misclassifications. Same way you have a blue point here. This is a misclassification. Underneath this is what is called the Logloss function. But what I'm going to show you is, what is this formula telling you? And please understand, we are giving a label of 1 to non-defaulters, 0 to defaulters. You could have done the other way around also, but this is what we are doing in this case because we are predicting probability of non-defaulters. Look at the formula and ignore everything. Come only to this expression. So the expression is yi into log of pi and then into 1 plus 1 minus yi into log of 1 minus pi. Sorry, pi, 1 minus pi, right? This expression. In this expression, now you look at, I'm taking 4 cases. What the first case is telling you is, for a given income, your model is predicting that the probability of him being non-defaulter is very high, and he is actually a non-defaulter. He belongs to the first class. You look at the code. Code is 1. 1 is given to non-defaulters. So in your, you know that this guy is non-defaulter, and your model is also predicting him as non-defaulter. So come to the equation. In the equation, you submit this yi is 1 into log of a very high number. Okay, when you log of a very high number, it's almost close to 1. Yeah, this is what you're doing here. Plus 1 minus 1 becomes 0, and whatever expression here will be 0. Yeah. So this whole expression will become 0. Log of a very high number is also 0. It tends towards 0. Log of a very high number, log of 1 is 2 power 0. This is log to the base 2. Log of 1 is 0 because 2 power 0 is 1. So this becomes 0, right? So overall your contribution to the error is 0. When you do correct predictions, overall contribution to error is 0. Now I've taken the first case, which is a blue case. I know he's a non-defaulter, so I'm given a blue. The model also predicts that he's a non-defaulter. So you come to this equation, you substitute this with the code. The code is, he's a blue case, so this yi becomes 1. Log of a number very close to 1 will be inching towards 0. So this whole expression comes towards 0. Come to this side, 1 minus 1 automatically becomes 0. We don't even need to evaluate this. So overall you have an expression very close to 0. So when you do correct predictions, the contribution to the error function is very close to 0. Take the red case. This case is case number 3, the red case. You know that the guy belongs to the 0th class, the red one, and the model also predicts him to be red class. So come to this point. So at this point for red class, this expression becomes 0. 1 minus 0 is 1 into log to the base 2 of 1 minus very small number, the probability here is very small. This expression becomes very close to 1, almost close to 1. So this also becomes 0. So whenever you do correct predictions of blue class and the red class, contribution to the error function is very close to 0. Take the case of this guy, the case number 4. Let's start with case number 4. Given his income, the model says he's likely to be a non-defaulter, but actually he's a defaulter. So this number for him is 0. This whole expression becomes 0. Come to this side. This expression becomes 1 into log of 1 minus a very large number. So very large number minus 1, this becomes a very small number. Log of a small number is very large number. So this becomes a large quantity. Whenever you do misclassification, you add a large amount of quantity magnitude to your error function. Take the case of blue class. As per the income, the model says he is likely to be a defaulter, but actually he is a non-defaulter. So come back to this equation. He belongs to blue class, so his y is 1. The probability value pi is very small. Probability of him being a non-defaulter is very small, so this number is a very large number. This expression becomes 0, 1 minus 1. So you contribute a very large number to the error space. So misclassifications, you'll contribute a large magnitude to the error. Correct classifications, you'll contribute a very small amount to the error, not 0, small amount. So in logistic regression, in multi-class classification, what happens is, in your mathematical space, you might be multiple S-curves cutting each other. In fact, right point to tell you, all algorithms, they create compartments in your mathematical space. They break your mathematical space into compartments, into zones. All algorithms do this, whether it's linear or non-linear. So maybe this compartment which you created here belongs to A, maybe this compartment belongs to B, maybe this compartment belongs to C. So it breaks all these algorithms, whether it's neural network, support vector machine, or logistic, or whatever it is. They break or decision tree, they break your compartment, mathematical space into compartments. So the optimization function here is a Logloss function. The overall objective is, by controlling the M and the C of the underlying equation, it tries to shift the curve forward, backward, upward, downwards, such that the overall Logloss function comes to minimum value. What is the value of M and C? Which will give me least log loss. Least log loss means more accurate predictions.